All right, hello everybody. Here we are at the beginning of chapter 7. It's going to be our last chapter we're going to wade into. We're not going to get through this entire chapter, but I am going to give you some pretty important stuff here at the beginning of the chapter. So let's begin. This is called higher polynomial functions. Well, what it's referring to is polynomials are things that have a variable and maybe an exponent. For a very long time, you have looked at linear equations. If you saw an equation that was y equals, say, 5, this is what we call a constant function. Constant. And it's a graph that is a horizontal line. 1, 2, 3, 4, 5. Sometimes we see linear functions that of the form y equals mx plus b, something like that. And this is a linear equation. They're called linear because they form lines also. This constant's really a linear equation too, but these are linear equations, and they will form lines. And you just need to know how to interpret all the information here. So we got a y-intercept, and we have a slope on it, and it's going to form a line. But you'll notice that x to the first power is what this has been talking about. We don't see that 1 that's there, but it's x to the first power. And then in chapter 6 we talked about this function here. I'll give you the most basic one here. It's x to the second power. And that always created parabolas. Sometimes those parabolas opened up, sometimes they opened down, sometimes they were shifted left and right, sometimes they were stretched and shrunk or whatever. But you'll notice that the x to the second has a different shape. Well, as we go to higher polynomial functions, what we'll find is that the bigger our exponent is, as this exponent changes, the polynomial function's shape continues to change. Let me show you what I'm talking about here. All right, here are those first two equations again. Again, this is x to the first, and of course you don't see the 1 there, and this is linear, and this is x to the second. This forms parabolas. We call these quadratic functions. But if we continue to make that exponent bigger and bigger, y equals x to the third, this is of course what's called a cubic function, and cubic functions look something like this. Okay. Now they may change quite a bit. They may dip down a little bit, but they basically have this little curve that might look like this. It has curve. We'll spend a lot of time on cubic functions. And then if we went to y equals x to the fourth, we're going to see a symmetry just like quadratics, but usually the corners are a little sharper on it, something like this. And if we went up to the next but by the way, that one doesn't really have a name for it. Y equals x to the fifth. We're going to find a graph that looks something, more like, like this or something. They continue to change and get more and more complicated. If we had y equals x to the sixth, well, we could get all kinds of stuff here. It could come in and move around a little bit and then go back out. There's lots of different things that can happen. And what we're going to do in this chapter is help you to recognize patterns so that you can look at a graph and kind of predict what the polynomial would be, or look at the polynomial and kind of predict what the graph would be. This is going to be a discussion of the degree of the polynomial and also a discussion of what we call end behavior, or in some algebra books they call it extreme behavior, end or extreme behavior of the graph. And so we're going to be talking about what happens to these graphs as you go in both directions, left and right. So let's take a look at what's going to happen here, okay? All right, at the top of 349 and also at the bottom of 348, there's quite a discussion about this whole thing. And I'm going to try to give you some patterns so you can see what we're talking about here. Now, as you knew from quadratics, that when a parabola opened up, the a term in the front, this a term right here in the front, was positive. And you notice that when the a term in the front, right here, was negative, it opened down. It flipped over. And we're going to see that happen on a regular basis. What this is going to say is that leading coefficient, the leading coefficient, in other words, that's the number in front of the highest term, the number in front of the highest term, is it positive or is it negative, is going to determine what the graph looks like. Let me show you what I'm talking about. If I had, for example, y equals negative 3x to the third, or let's start with positive, that would be different than having y equals negative 3x to the third. Let's go ahead and see what would happen. 3x to the third would look something like this. And a negative 3x to the third is going to actually flip over this way. Now let's discuss that for a minute. If this leading coefficient is positive, the graph is going to enter in the south and it's going to leave in the north. When I say enter, I'm saying working from left to right here. It enters in the south and it leaves in the north. Well, vice versa over here, as you go from left to right, a negative coefficient is going to come in, enter in the north, up here at the top, and it's going to leave in the south, down here. Now that always happens, that the leading coefficient tells you if it's positive, it's going to open one way, if it's negative, it's going to open the other way. And as you study those pictures on the top of this page, you'll discover that those coefficients determine whether the thing is going to open up or open to the right or whatnot. Okay? So the first lesson that you need to learn is take a look at the sign of the leading coefficient. Now this is true of every polynomial. So let's say, for example, I had y equals 2x to the fourth and y equals a negative 2x to the fourth. Well, what I can expect here is that the polynomial, when it has a positive exponent, it's going to open a certain way. Not an exponent, excuse me. When it has a positive leading coefficient, it opens up. And when it has a negative leading coefficient, it will open down, just like parabolas. So those signs determine which way these graphs open. It causes them to flip over, just like we saw with quadratics. A positive leading coefficient and a negative. They're one's opening up and the other's opening down. Here it goes from south to north versus north to south. So as you look at the top of 349, you can see that that's discussed up there in great deal. This is what's called the end behavior. What happens at the end of the graph? Is it going to come in from the north and leave in the north? Or is it coming in the south and leading in the south? And so this is the discussion that's going to happen in this chapter, and your ability to predict what's going to happen to the graph by looking at that leading coefficient. Whether it's positive or negative will determine that. All right? All right. Now, with just a little bit of study on those same pages, page 349 at the top, you'll discover that whether the exponent is odd or even also makes a difference on your graph. Let's take a look at the pattern that we see here. If the exponent is odd, for example, here's an x to the first, you'll notice that the graph is a line, looks like this. And if it was a third to the third power, that's an odd exponent as well, we expect that it is going to look like this. And if it was another odd exponent, let's say x to the fifth, we would expect it to look something like this. You'll notice in all of these cases, when the exponent is odd, it leaves and enters, it enters and leaves in a different hemisphere. This particular problem, these that I'm showing you here, enter in the south and leave in the north. Enter in the south, leave in the north. Enter in the south, leave in the north. That's because these have odd exponents. Now, on the other hand, if we had an even exponent, like 2, 4, 6, 8, well, let's see now. This would be a quadratic, and it enters and exits in the same hemisphere, north to north. Y equals x to the fourth. Again, an even exponent. It's going to enter and exit in the same hemisphere. Starts in the north, ends in the north. And even if I change the sign out in the front, say x to the sixth, even exponent tells me it's going to enter and exit in the same hemisphere. Now, because this is negative, it's going to come in down here. And it'll look something like this. Okay? Enters in the south, leaves in the south. The even exponent tells you that they're going to leave in the same hemisphere. And if it's an odd exponent, they enter and exit in different hemispheres. As you study those and try these problems, you'll see that's what's going on here, is this combination of, is the exponent even or is it odd? And is the coefficient in the front negative or positive? Well, let's try a couple of these so you can see how you would evaluate this in the middle of doing some homework here, okay? All right, let's see if we can determine what the end behavior would be on a graph like this. Now, the only thing that matters to us is that the leading coefficient and the leading exponent are what we're looking at, just these two things. Now, the leading exponent, 3 in this case, it's odd. And that tells me that if it comes in the south, it's going to leave in the north. Or if it comes in the north, it's going to leave in the south. Which of these is it? Because odd exponents tell us they leave in different hemispheres. Well, the answer to that is this sign. That's the leading coefficient. Now, I could put a 1 there or a -2 or whatever. It doesn't matter the number. What matters is that sign. If that sign is negative, then it's going to be leading in this direction. Notice it's coming in here and it's going out down here. It's almost like it's got negative slope. You see the negative slope here? It's kind of leaning downhill. If this were a line, that'd be going downhill. Well, negative slope causes it to kind of have a negative lean to it. Okay? So the exponent tells us that it's going to leave and enter in different hemispheres, and the leading coefficient sign tells me which of these it is. You know, it's got a negative slope. This one would have a positive slope. Okay? Let's try another one. Come back and look at that again if you need to. All right, let's take a look at this one. Now, the only thing I'm concerned about is this leading exponent and the sign. Well, what you don't see here is a plus sign. So I'm only concerned about these two things in an effort to understand the end behavior. The end behavior. Well, since it's an even exponent, I know that it's either got to come in the north and leave in the north, or it's got to come in the south and leave in the south. One of the two. Even exponents mean they're going to leave and enter in the same hemisphere. Well, that makes sense. They're symmetrical. And this reminds us of quadratics, right? Well, because this one comes in the north and leaves in the north, it's going to open up, right? It's going to open up because it's a positive. If that were a negative, this would open down, right? This one were a negative coefficient, this one were a positive coefficient. This one, these are both even because they enter and exit in the same hemisphere. Let's look at another one. All right, let's see if you can get ahead of me on this one and figure out what's going to happen. Well, we're only concerned about two things: this leading exponent and the leading sign. Well, it's an odd exponent, so that means an odd exponent either has to enter in the south and go out in the north. They're odd, kind of like different. Or it has to enter in the north and go out in the south. Well, which is it? And then now we look at the sign here, and it determined that, oh, this sign is negative. That means it's going to have a negative slope, and that would be this one. It's got a negative slope. So it's coming in here and it's going out here. It's got several bends to it. Okay. Now, at this point, we're not going to talk about the number of bends that it has, but that's something that will come up in the next video. But right now, we're just looking at the leading coefficient sign and the leading exponent. Let's do one more, and then I'm going to move on to the other topic here for today. All right. One thing I need to mention here, we didn't talk about it, is that they may not be giving these to you in descending order. Usually we write them in descending order, but they may not give them to you in descending order. So which of these is really the leading term? Well, it has to be this one, because the exponent is the biggest exponent. So if I was to write this again, I don't really need to, but if I was going to write this again, I could rewrite it in descending order like this. Now you can see that this is the leading term. They're in descending order. It's x to the sixth, x to the second, x to the first, and so forth. Okay. Now I'm looking at whether the exponent is even or odd. Well, it's even, and even exponents mean that they enter and exit in the same hemisphere, either north to north or south to south. Well, which is it? Let's look at the sign in the front. Oh, it's a negative sign. That means, like parabolas, this is going to open down. Okay? I don't know, I probably got too many bumps in there, but it's going to have to open down. So this has to be the graph we're talking about. It's even, and the even determines whether or not it's entering and exiting the same hemisphere, and the negative determines that it opens down. Okay? It opens down because of that. Okay? Now, you'll have to practice those a little bit to be able to determine what's what. Now, let's try it the other way. Let's go look at a picture and see if we can figure out what the power might be. All right, here's problem 13 from your book on page 350. And it's asking for you to describe the end behavior. Okay? They have a certain way of talking about it in your book. You can use that terminology if you can figure out what it means there. Or you can just say, well, it enters in the north and it leaves in the north. So this one enters in the north and it leaves in the north. Okay, so you can just say that. The way the book discusses this is it says, as x goes to a negative infinity, in other words, out this way, y goes to a positive infinity, in other words, up this way. Or as x goes to a positive infinity, out this way, then y approaches a positive infinity, in other words, up this way. That's the way the book is describing this. That's not a bad terminology, and as you get deeper into math, that's going to be more helpful to learn that. Now, it's also going to ask you whether or not this, how many zeros it has. Well, this one has no real zeros because it's not crossing the x-axis. So I'm going to write that down, no real zeros. And it tells you what, it asks you what possible exponent could this function be. Well, sometimes we know that it's going to be even. So it's either x to the second, or x to the fourth, or x to the sixth, or x to the 8th. Now, it could be any of these except for the fact that we know that x to the 2nd is a parabola and it only have 2 zeros. Well, this would have, if this had any zeros, it would have more than that. Plus, I can tell by the number of bends here that it's got to be higher than 2. Let's see how many bends it has. 1, 2, 3, 4, 5 bends means that it could potentially have 6 bends or more. Excuse me, it could have 6 zeros or more. You count the number of bends and say, well, you know, I could have a 0 here and here and here and here and here and here. I could have six zeros if this was shifted down. So you're going to look at the number of bends to decide, well, it's got to be at least a 6th degree polynomial. If you're not sure, go ahead and put it in your, put a 6th degree polynomial, maybe in your calculator if they give you one. You can kind of check that out. This is a little harder to determine, but you've got to look at how many bends it has. This can't be a squared. It can't be x to the 4th. It has too many bends in it. Let's look at another one of those, okay? Okay, number 14. Well, first of all, let's determine if this is odd or even. Well, it starts in the south, comes in the south, and it leaves in the north. That makes this an odd function. So it could be x to the 1st, maybe, x to the 3rd, x to the 5th, or higher, could be even higher, okay? Well, I know it's not x to the 1st because x to the 1st is a line. So it can't be x to the 1st. And it looks like it's only got maybe 2 bends in here, 1, 2. And so it's very possible that it's x to the 3rd, but it could be higher. So I'm going to say it could be x to the 3rd or higher. Could be higher than that, oops, but it may not be. But it's at least x to the 3rd. Okay? Let's look at another one of those. Okay, here's problem 44. My graph's not that great here of it, but there it is. Now, I can see that it enters in the south and it's leaving in the south. Well, that's an indicator that this has to be an even function, has to be even. And as I look at it, it's got 2 real zeros. It's got 2 real zeros, but it could have some imaginary ones too. And I'm going to look at the number of bends. It's got 1, 2, 3 bends. So it could potentially have zeros here and here as well. So I would say that this thing, so it's got these 2, but it could potentially have 2 more. So I would say this probably has to be x to the 4th or higher. Could be higher than that. Could have, more zeros in it than just the 2. If this thing was shifted up, it might have 4 zeros right here and here, okay? So you practice that for a little bit, spend some time on that, and let's take a look at the other topic in this chapter, this section. All right, there's another type of problem in this assignment that I want to call your attention to. You may have recalled that this is function notation. This is p of x. It does not mean p times x. It's p of x. This is a function. We could call it y if we wanted to, but p of x is equal to this function. Okay? And if you recall, when it's asking for p of 4, it's saying what would p of 4 be if we stuck 4 in for x in every place that it appears. Now, you could do this manually if you wanted to. I'm going to show you how to use the calculator here. You could take that 4 and you could stick it in here for x, and stick it in here for x, and stick it in here for x. And you could do all of this arithmetic, heaven forbid, there's a lot of arithmetic here, and calculate what p of 4 is. But it's so much easier just to do that with your calculator. So let's go and show you how to do that with your calculator, okay? All right, I've gone to my y equals screen, and I've plugged in that equation. Make sure you're using all the correct notation and everything, make sure you use the subtraction signs and not negative signs in these situations. Put your exponents there, check it out real carefully. And we're going to go ahead and graph this. Make sure you turn your plot off or you'll have trouble there. We're going to go ahead and graph this, and because the numbers are all relatively small, I'm going to start by trying to graph it in a standard screen. So I'm going to press zoom. Here, let's move this up a little bit. I'm going to press zoom right here. Zoom standard. See what kind of graph I get. Well, there's some stuff going on. All right, now let's go back and look at the graph again. What do we expect to happen? Well, this is very helpful because sometimes when you graph something with your graphing calculator, you may not see the whole thing, but let's see what we should expect. I should expect an even function, so it should enter in one hemisphere and leave in the same hemisphere. And also, because this is a positive 1 out front, I should expect it to come in the north and leave in the north also. Let's see if that's what happened. Well, it appears to be that's what happens. I can't tell what's going on at the bottom, so I'm going to zoom out with the window a little bit. So I'm going to lower my window. I'm going to press window, and let's take the Y minimum down to maybe -20 or something and see what we get and graph it again. No, I still didn't go down far enough. Let me go down a little farther. Window. Let's go down to negative, just to be sure, let's go down to -50 and graph it again. Why? I'd have to go down even farther. But the point is we can see that this does enter in the north and leaves in the north. That means it was even function, okay? And because it opened up, they're both going up, this is a positive. And that's what we know to be true looking at this equation here. So x to the fourth, it opened up because it was positive, and it entered and exited in the same hemisphere because it was an even exponent. Now, we're going to get away from your picture for a minute. I mean, we could look at this picture and try to calculate it, but it's way easier to come up with. Remember, what we were trying to find was P of these two numbers here. Let's go back up. I wanted to find P of 4 right here and P of -2. Well, that's so much easier to do by going to table. So let's go to table and see what happens in there. So I'm going to go second graph, that's table. And here's a table here that all I have to do now is look in the X column for 4. P of 4, that'd be right there. If X is 4, I get -166. If I plugged in 4, which is what we're finding, P of 4, right? P of 4 would be -166 right here, okay? So you don't really need to plug all those numbers in to make the calculation. Let's do the other one. P of -2, I'll just move your cursor up there to -2. There it is, -2. If you stuck -2 in there, you would get 50. So the answer to these two problems, P of -2 was 50, and P of 4, we said, was 166. So this is very easy to do with your calculator. Let's do another one, okay? All right, here's problem number 29, and this looks like it would be an overwhelming task to find P of 4, to stick 4 in there in all the places and try to do the arithmetic here, especially with these fractions. So if we use our calculator, we can just stick everything in. And so I'm going to do that. I'm going to plug this into the calculator here in the y equals screen. So let's clear it out. I want you to do it with me while you're doing that. Let's make this a little bit larger so you can see it. Okay. Now I'm going to type in 1/8, but I don't want to use any rounded numbers, and maybe I don't know what 1 divided by 8 is. I could probably calculate it, but I'm going to go 1 divided by 8, and it's okay here to not use parentheses because your calculator, if you're going to multiply right now, and we are, it's going to put that next thing on the top instead of on the bottom. It looks like it's on the bottom. And if you're not sure, just go ahead and put parentheses around it just to make sure. 1 divided by 8, and then times x to the third, minus, and I'll put parentheses here although I don't need them, 1 divided by 4, 1/4 x squared, minus 1/2, well I know that's 0.5, so I'm just going to enter 0.5, it's easier, x plus 5. So if you know the fraction or the decimal, if you know the decimal for it, you could stick that in, it's usually faster. Now you'll notice that I've got the function typed in here correctly. Make sure you're using subtraction signs and not negatives in all those places. Now we could graph this. We don't need it here to do the problem, but let's see what happens if we zoom standard again. All right, just by way of discussion here, notice that we had an x to the third function with a positive leading coefficient, and that's what we're expecting. It enters in a south hemisphere and it leaves in the north hemisphere. So that's what I expect from an odd function, and because the slope is negative here, or excuse me, positive, I expect it to be leaning to the right. So that plus sign out in front of the 1/8 is telling me it should lean to the right here. So anyway, that's just a little reinforcement. You can tell when you've graphed something if maybe some of it's not showing on your graph by looking at this end behavior idea. You need to be able to tell that. That's not something that the calculator is going to help you with always. All right, let's see what happens if we use the table here. So second table. And we want to define P of 4. Okay, well I'm just going to go down to 4. If x is 4, y is 7. And then if x is -2, y is 4. So this is really easy to use the table here to do that. P of 4 we said was 7, and P of -2 is 4. So this is the easy part of the assignment, but make sure you understand how to be able to predict the end behavior of these graphs. Go back and watch this a couple times and look at the problems on the previous pages, the examples and so forth. Because the next section we're going to kind of move on from here a little bit. All right, here's your assignment for tonight. All right, so there's the assignment for tonight, and you've got a little bit of both kinds of problems here. This section 22 to 30, 22 to 29, I believe, is being able to find the value of what would it be if you put a number in table. Use table for those problems on 22 to 28 or so. Okay. Do the best you can on this. Make sure you do understand the end behavior. That's the critical part of this assignment. All right. Catch you next time.